Welcome back. Today we're going to talk about cylinders. In passenger cars and most internal combustion engines, you have a couple different types of cylinders that can be used. And it's going to depend on the type of casting or type of material that the block is made out of and what the manufacturer wants to do. So as we know, engine blocks are primarily going to be made out of cast aluminum or cast iron. There are some cast magnesium blocks, but cast aluminum and cast iron are the two big front runners when it comes to the population of blocks. And we're talking about, OEM stuff. There are aftermarket blocks that are going to be billet aluminum, so they're actually machined out of a solid block of aluminum. And but we're not, the same concepts apply, but they're almost always going to use one type of cylinder, and we'll talk about that in a second. So the different types of cylinders, I've got three laid out here, and really there's two groups where we have these two over here on the right and then this guy on the left. But the fourth one that's not in the picture is going to be used in primarily cast iron blocks. And it can also be used in aluminum blocks too, but those are, I wouldn't say rare, but there are a lot fewer cases of them out here, especially here in the States. Is an integral sleeve, where the cylinder sleeve, the cylinder material is of the casting material of the block. So if you have a cast iron block, all the manufacturer needs to do is bore the cylinder out of the cast iron material. And then of course they do the proper dimensioning and then the surface treatment on the cylinder, and they've got a perfectly usable cylinder. And that's how a majority of, I would say, all gasoline engines with cast iron blocks are going to be using that integral type of cylinder. So the other style, and it's still integral, is going to be on aluminum blocks. Now in aluminum blocks, they've got 2 or 3 different routes to go, and one of them is coating, and then the other one is actually using a different material in the aluminum. So if the manufacturer decides that they want to have an integral cylinder in aluminum block, they can actually have the cylinder coated. And they can coat it with something called Nicosil, or there's Alusil. These are all different coatings that can actually be applied to the cylinder, which will create a hard bearing surface for the piston and piston rings to slide up and down on. The other style would be to use a high silicone content aluminum, which creates a hypereutetic cylinder, where instead of the silicone that's normally floating around there in small pieces in the grain of the aluminum, they take it to where it's super saturated, so the silicone actually creates much larger crystal, or much larger nodules basically. And the machining process of the cylinder is not necessarily honing, or it's not cross-hatching. What it is, it's an erosion process to where the aluminum, which is holding the silicon particles, is worn away so that the silicon particles are proud to the surface, and the recessed section in between all the silicon particles is where the oil lies, which allows for piston ring sealing and lubrication of the rings and the piston skirt. So those are the integral styles, where you can have it just machined out of cast iron, and then you have coated aluminum, and then you have a proprietary, like a high silicon content aluminum blocks, so that they can run the pistons right against the aluminum. And as far as I can remember, I want to say BMW does it, and Porsche does it, and Honda also did a version of it, and they called it FRM, which is fiber reinforced material. I believe that's what it is. Might be wrong. So here we are with the ones on the table. So the two groups that I've got here, and these two right here are actually OEM piston or cylinders. And the difference between the two is pretty obvious when we look at this right here. So there's a little ring right there at the top, and that's actually a sealing ring, and this one doesn't have any rings or anything in it. So this is what's considered a wet liner. And so the outside of the wet liner is exposed to the coolant of the cooling system. So it provides a really good transfer of the heat energy from the cylinder and the combustion that happens inside to the coolant to then get it out of the engine and then off to the radiator to be expelled out to the cylinder, or out to the air. So this is a wet liner. And again, wet liner means that this outer surface is going to be exposed to coolant. So these right here are actually pressed in place, and there's not a lot of force. It's just O-ring force here, and then if I remember right, there's actually 2 O-rings down here at the bottom. They're located in the block, and this just gets pushed down into the cylinder, or into the crankcase, and you have your cylinder, and everything's ready to go. And when you're rebuilding this engine, this actually came out of a later model Porsche. You can machine this, and you can also have these cylinders replated, but it's actually not too expensive just to go buy new cylinders and new pistons. And then all you have to do to rebuild the short block is to replace the pistons and replace the cylinders. There's very little machining involved. But that's just how that they do it. Now this is an aluminum parent material, so most of this is actually aluminum, and then there's a coating on the inside that is, if I remember right, a silicon carbide coating. So this coating is really hard. So honing it is not going to be using traditional honing abrasives. It's going to be a super abrasives that are going to be required to cut it. So we have a wet cylinder, and if we've got a wet cylinder, that means that we're going to have a dry cylinder liner. So this one's going to be dry. And as you may have guessed, because this one's exposed to coolant, this one is not. So this cylinder is pressed into the block. It's either pressed, or they'll heat the block up and freeze this and then drop it in. But this is in the block, but it is in contact with the block material from the very top all the way to the very bottom. That means the heat interface is the piston combustion chamber temperature has to go to the sleeve, and then it has to go out to the parent material of the block, be it cast iron or aluminum, and then it has to go to the cooling system. So that interface between the origination of the heat out to the cooling system has to take a couple steps. This one is one step. This one, it's got to go to the sleeve, then it's got to go to the block, and then it can go to the cooling system. But dry cylinder liners are, really there's 2 different types from the OEM. So this one right here is an interference fit cylinder liner. That means the block, the aluminum block, is machined to accept this, and then this is installed after some preliminary machining. On GM V8, the LS, and LT engines, not all of them, but some of them, they are cast in cylinder liners. So that cylinder liner, like this one here, has very little features, actually very smooth on the outside. That cylinder liner actually has ribs cast into it. So before the engine block is poured, they position these in the casting, and then they pour the aluminum around it, so the aluminum comes in and it actually grabs onto the ribs and the features on the outside of the sleeve. And what that does is, one, it holds the sleeve in there very well. And second to that is it creates a lot of surface area, because if I've got a cylinder that's just this straight, I have so much surface area. But if I want to increase the amount of surface area for heat transfer, if I put a rib in there, that means I've now got the radius of that rib around the circumference of the sleeve, so it increases surface area, increases contact patch between the sleeve and the block material to help get rid of heat. So we've got our wet liner and then our dry liner. Now this one here is really, it can be a dry or it can be a wet. This one happens to be a dry liner because it has no sealing rings up at the top or the bottom. But this is a straight sleeve, so this one is just straight from top to bottom, so it has no flange, no nothing, it's just straight top to bottom. And then this cylinder is a flanged sleeve. So this one contacts the parent material of the block, be it cast iron, aluminum, or magnesium, And you have to have a good interface between this cylinder, OD, and the spot on the block where it goes for heat transfer, but it's not going to be retained by this interference fit. This one here, if we measure the outside diameter from here to here, and then we measure the hole that it went into the block, this would be about 2 to 3 thousandths larger. Now they have to do that because that's what keeps the sleeve in place. If this thing just slipped and fell right in on its own, this sleeve would have a tendency of hopping up and down because the piston would be stroking up and down inside there. And that little bit of friction, even though it's supported by oil and piston rings and piston skirts, would cause this to oscillate up and down. And if this were mounted in aluminum, aluminum is pretty soft compared to this cast iron material, and the sleeve would actually drop from the deck of the block. So it would be head gasket, it would drop down just slightly, and you could have a head gasket failure. So to help prevent that in high horsepower applications, we use flange sleeves. So this one's got a flange on the outside. So the block is machined for a larger outside diameter because going from this one to this one's bigger by about 100 thousandths of an inch. But then I also have to machine a counter bore, and that counter bore is where this flange is going to sit down on the top of the block. Now, there is some interference fit on this, and really that's for heat transfer, but the retention of the sleeve is going to be done by the top of the flange, by the flange here, because it's sitting on a ledge on the block, and then the cylinder head and head gasket are pushing down on the top. And that's what's going to retain this sleeve to keep it from moving up and down. Now when flange sleeves are installed improperly, they are not seated fully down against the counter bore for the flange, and when the engine runs it gets hot, not overheating, but it gets up to temperature. We've got the piston going up and down, and we have the combustion temperature where the block expands, and this will drop. It only needs to drop say 3 to 5 thousandths minimum for it to cause a problem with the head gasket. And then you'll start to have high pressure in the cooling system, or you could have water leaking into the cylinder, and you have white smoke out of the cylinder. So that's our sleeves. Next thing I'd like to get to is talking about machining of the cylinders. So let me get that set up and we'll be back. And we're back. So to service a cylinder, we really have a minimum service that we can do on them, and there's the full service on a cylinder. And the other thing is that if we've got a V8, we're not just going to machine one cylinder oversized for one piston. If there is excessive wear in a cylinder, if there's scoring in the cylinder to where we can't reuse the original cylinder size and the original piston diameter, we have to install a larger piston, then we have to machine the cylinder. But we're going to machine all of the cylinders on the engine so the power and the compression are balanced throughout the engine. It's just part of service. So we have a cylinder, and we did our measurements, and let's say like on our LS or our 5.3, we had 4.5 thousandths piston to cylinder wall clearance when the maximum service limit is 1.5 thousandths. So we're 3 thousandths oversized, and we want to make this engine run perfect. We're going to machine this cylinder larger so that we can put in a larger piston. So before we get to that, if we're disassembling an engine, and let's say that we're pulling it out because, I don't know, we're replacing maybe we're just replacing the connecting rod bearings or the piston rings for some reason. Maybe it's consuming a lot of oil and the rings just need to be cleaned out. The piston ring grooves need to be cleaned out. And just replacing those would be good. Well, there's a minimum service that you want to do to the cylinders if it's a cast iron liner, and that would be to deglaze the cylinder. So I have a cylinder here that it's heavily glazed, and now it does have rust here through the section, but that's not really what I'm looking at. What I'm looking at is how shiny this section is right here. So this shiny section means that this has been polished down, and it's been polished by the piston rings rubbing on it. And it's so far polished that the cross hatching is still evident, but it is not deep enough to hold oil. So what we want to do is deglaze this cylinder. Now the way that we deglaze it, and there's a couple of tools, and I've got one of them here, is to use something called a flex hone. So this is mounted on a wire shaft here, and each one of these little nodules is an abrasive. It's either aluminum oxide or silicon carbide. It depends on the model that you get. There are different diameters available. So this guy is basically just a big old sandpaper tree, and you're going to shove it in the cylinder, and you're going to turn it on a drill, and you're going to stroke it up and down. Now it's very difficult to make crosshatch with this, with a slightly oversized or undersized ball hone, but you can. But you have to spin it at about 100 to 150 RPM while stroking the drill up and down inside the cylinder. There are some other videos online where somebody starts the drill and they just start it going and they're just hanging out down there at the bottom, and they slowly pull it out of the cylinder. And what that's doing is creating a whole bunch of horizontal scratches. And horizontal scratching is not cross-hatching. So you put this in the cylinder, you turn on the motor, a slow speed, and you're going to stroke it up and down to hopefully get about a 45 to a 30 degree angle on the cross-hatching in the cylinder. And this is deglazing. This is not for correcting any dimensional issues. It's not going to fix a cylinder that's too small in the bottom. Trying to make it bigger with a ball hone, that is not going to happen. The other style of hone is a spring-loaded 3-stone hone. I don't have one here. I'll do an overlay on the video. And those 3-stone hones, they call them hones, they're really glaze breakers. They're going to do exactly the same thing as this, but with a 3-stone spring-loaded hone, it is a lot easier to establish a crosshatch. This guy right here, you can do it. It's pretty difficult. I wouldn't say difficult. It takes a little more skill. But the 3-stone hone, you can definitely do it with a little bit of time. Same thing, you're going to run it about 100 to 150 RPM while stroking this guy up and down inside the cylinder. If your drill can't go that slow, you're going to have to stroke pretty fast. But make sure that you don't run the hone down too far and hit the mains and break your hone. So we want to do that. Now either method, whether it's the ball hone or the 3-stone spring-loaded one, you've got to flush it. And WD-40 works really well. And you're not lubricating the stones so much, but what you're doing is these abrasive pieces right here, they need to get the iron that's removed from the wall off of them. So while you're honing or glaze breaking, you're going to be hitting this with WD-40 or some other light lubricant like that. Like you could use kerosene or diesel oil. Either one works because it's going to evacuate the cast iron that's been cut off the cylinder out so that this abrasive will work again. It's kind of like trying to get a truck unstuck out of mud when the tires are packed with mud. You ain't going to get any traction. So that is kind of the same thing. All right, so that's glaze breaking, and if you're just going to pull a piston out, put new rings on it, and put it back in that same hole, a glaze breaker is a great way to go. And it is a very minimal thing to do, and everybody's going to do it in their life if they worked on cars. Now, the next thing we have is actually a series of steps, which can start from the extreme here and go all the way over to this guy. Now, these are both manual methods, and this can actually be integrated into a machine. So we need to take this cylinder oversized by 0.5 millimeter or 0.03 of an inch or 0.06 of an inch. We have to oversize the cylinder. To do it with a ball hone would take you forever, and it would also not be very straight at all. So what we would do is a machine shop would do, and I guess you could do this at home, but it would take a long time by hand, would be to oversize the cylinder. Now traditionally what's been done is we've machined the cylinder using a boring bar or a boring head or a boring stand, but a machine shop would actually machine the cylinder out so it would be bigger. So if we're going to take the cylinder out to say 30 thousandths of an inch, we're going to use this guy to basically cut away the material not to 30 thousandths, but we're going to cut away about 25 thousandths of the diameter. And we're going to leave that last bit for final dimensioning and surface treatment. So we have our boring head. Just like in the boring video, this guy right here, this spins around while it plunges down into the cylinder, and it's basically threading with a very fine thread the cylinder. So this section of cylinder here has been bored. It's the same one as this. I actually bored it out and then broke it so that we could have it for illustration purposes. And I'll put this under the microscope in a minute when we talk more about it. But this has been bored out. And this surface right here is much too rough to be running piston rings against. We have a finish that is probably 10 times rougher than it should be. If we were to put a modern piston with modern rings against this, those piston rings would probably last about 2 to 3 seconds of engine RPM. The piston, it would be done before then. It's much too abrasive. So we have our bored surface right there. Then we go from boring over to honing. Now this is a manual hone, and what it has on it are, looking from the end, we've got these two shoes here, and these are what's called guide shoes. And then we have these two over here, which are the actual abrasives, and they expand on the head. So you can see, if I can get this set up right. There you go. See how they're expanding out? So the machine shop would fix that, put it down on the cylinder, and then they would expand it into position. Let me see if I can get that expanded again. Okay, so we're pretty close, and then this is our fine adjustment here on the end. Of course, we're going to do this with this cylinder in the block, and it's going to stroke up and down while it's spinning. Now this one here, I've got it set up just so I can run it on a 1/2-inch drill, and I do this on lawn mowers. I'll do this on any time that I need to change or just put a small crosshatch in the cylinder. I prefer this method because the crosshatch is a lot easier to produce when your abrasive is like right there. So what this abrasive is, it could be aluminum oxide, it could be silicon oxide, but it's basically sandpaper in a brick form, and it's bonded to this this shoe right here, and it's being held out on basically a rack and pinion setup. So while you're honing, there's pressure on these stones pushing out against the cylinder. And as you're honing it with this manual method, you have to turn this adjustment nut right here, just turn it just ever so slightly to create tension. And then you're going to stroke it up and down, and then add a little bit more. Now, to machine a cylinder using this manual method, if you wanted to try and machine a V8 block, you could do it. But to go out even 5 thousandths on a V8 block, it would probably take about 20 to 30 minutes of manual honing with, you know, a 1/4 horsepower or 1/2 horsepower drill. It would be a lot of time and a lot of effort on your part, and that's for one cylinder. All the while having to take it out, measure the bore, and then gauge your progress to see how much more you have to do. But this is honing, okay? This is what has to be done, the final process to put the cylinder to dimensions and also establish a crosshatch. Now, back in the 80s and 90s, but machinists or engineers, one of them, had an idea, because even though this is a bored surface, you know, this has been machined and it's very rough, honing looks like this but on a microscopic level. Because what the hone is essentially just a collection of a bunch of rocks that are being dragged through the aluminum. And when you drag, or not the aluminum, the cast iron, and when you drag anything through cast iron, you create fractures on the surface. Those fractures are loose pieces. Well, in the fractures, there are loose pieces of cast iron, and we'll actually see it pretty obviously here. I don't have a high power enough microscope to do the honing fractures, but the fractures on this surface have material on them so that when the engine runs for the first time, the fractures break off. So engineers and manufacturers and machinists, they came up with a process called plateau honing. And plateau honing is a semi-abrasive brush. So this is a nylon brush that has a very fine abrasive impregnated into it. And all this is going to do is basically go up and down in the cylinder. You don't have to worry about crosshatch. You're not establishing crosshatch with this. And with a honing oil, you're going to stroke it up and down inside the cylinder, and you're basically breaking off all of the fractured material that could be broken off by the piston rings when you first start the engine. Now, back in the old days, and it's still evident in some machine shops nowadays, it was very common to a customer that had a new engine that had been rebuilt. The first oil change, the oil was gray. And the reason it was gray was because all the honing material that was still left on the cylinder, and you can scrub it. You can hit it with brake clean, you can hit it with gasoline, I don't care what it is. It's not going to come off until the piston and the rings stroke up and down inside the cylinder. And that's what they called bedding in piston rings back in the old days. All that stuff falls down to the pan, and it's all cast iron. So when manufacturers decided to start using a plateau honing process, it knocks all that stuff out in manufacturing or in the machining, so that the first oil change isn't gray anymore. The first oil change is nice and golden like it should be, because everything's sealing and everything's working perfectly. So we have our plateau hone. Now, they do have different sizes of these. Like this is I want to say it's a 3 3/4 up to a 4 1/8 size. So it can be used on more than one cylinder to plateau hone the cylinder. Now, what I'm going to do is bring up the cylinder samples on my microscope. So here's the first one. I have a section of glazed cylinder, and then you see in this cylinder there's little brown marks, and we're not worried about the brown marks. That's just rust from the block being stored. And you can see cross-hatching in there, but I just want to give you a little bit of scale. What I'm going to put in the picture is the tip of a pencil. So there's the tip of our pencil. That's the graphite, and there's the wood. So this is the scale of what we're looking at. Those little scratches inside the cylinder, that's cross-hatching. And notice there's an angle between the ones that go in the positive slope and the negative slopes. Let me try and get my pencil back in the picture. So we have scratches that go from this way down. And so that would be our negative slope scratches. And then our positive slope scratches. The angle in between them is going to be that crosshatch angle that is specified. This is a glazed cylinder, and this cylinder, these cross hashes, if I can get the words out, cross hatching is too shallow. It's not enough to hold oil. So the the piston rings will not have enough oil between the cylinder wall and themselves to seal. So this glazed cylinder will have low compression, and it's because of the depth of the cross-hatching. So we're going to jump from the glazed cylinder, and we're going to look at the bored cylinder. So let me get this into focus. All right, so in the bored cylinder, what we're looking at is those horizontal lines are from that triangular bit spinning in the cylinder and machining away the material. So if I get this focus, there we go. Now what we see, get my pointer back in there, the lines that go horizontally in the video here, those are actually the grooves that were machined by the triangular bit. All that trash in between, the kind of the yellow and the brown and blue kind of in the picture there, that stuff right there, right at the tip of the pencil, that's all fractured cast iron. because cast iron's got a grain structure, well, let's say it kind of looks like particle board or OSB, oriented strand board. So when that bit is drugged through the cast iron, it's kind of like breaking a whole bunch of grains, and it breaks it out. And those pieces are very close to being they're very close to being broken off, and it wouldn't take much to knock it off. So what I'm going to do is try and get my pick over here, and we're going to see if any of them are loose by just dragging it next to them to see if any of them are going to move. So here's my pick. Oh, nothing moving there. I'm just trying to use magnetism. Oh, there it is right there. So that one over there on the left side, that piece that's moving, and it's moving because of magnetism. Now, this is a very small amount of magnetism. If it can move that piece, imagine what the piston ring will do as it swipes up and down on this cylinder. And this is a bored cylinder. Now in one section of the cylinder, I have abraded it slightly, similar to honing. So there we go, we've got all the same trash in the grooves. And then I'm going to go down to this section, and we can see that the trash is, not that it's gone, but the tops of it are flattened off. And what that's done is helped to reduce the amount of material that's in there. And this is essentially the beginning of honing. I did this manually. There was no other reason to do it other than for demonstration. But you can see that we go from, say pre-honing to the very first stages of honing. We can see that that material has started to clean up some. Now the next piece that I have is a honed cylinder. This one's been honed. Let me clean it up a little bit. And we can see the cross hatching in there. All right, so let's back off or focus. There we go. Let me try and get a little bit better shot of that. Come up some. There we go. Okay, cool. So I've actually backed off about 1/4 inch from the picture, so we'll see the size of the pencil. The pencil's dimension is kind of reduced a little bit just for scale, and we see that this cylinder has cross-hatching in it. And this cross-hatching is deeper than the glazed cylinder. There's also seems to be more of it, because you see how many scratches there are in the cylinder compared to that glazed, the glazed cylinder. The glazed cylinder seemed like there's more space in between the cross-hatching than was, so here's the glazed cylinder. And you see there seems to be, quite a few, but not as many as a freshly honed cylinder. You see all those scratches, all those parallel lines that are running in this direction, from the top left down to the top right, and then same thing, they got a whole bunch going this way. And all those scratches are, that's basically the abrasive on the hone head going up and down inside the cylinder, and those abrasives are wearing away cast iron. So that's, cylinder treatment, that's machining. So we've talked about deglazing, we talked about the cylinder boring, and cylinder honing and plateau honing. Now let me try something. I want to get out a honing stone. Let me wipe it off. And we're just going to see if we can see something on it close up. And one thing I didn't talk about was the grit that's available. So if you have any experience with, any experience with sandpaper, you know a little bit about grit, which is, the number of points per inch here in the States. So here we have our, got some fuzz from a paper towel in it. So we've got the actual abrasive here, and we can see this is an aluminum oxide one. So we do have sand in there, and it's what's called vitrified abrasive. It's actually pressed together and cured into the shape. And we see, of course, there's those little filaments. Those are just from the paper towel that I used. But I'm rubbing, I think I'm writing all over this thing.
What I'm trying to show you are the little yellow pieces, and then there's also some light tan pieces, and then there's some black pieces in there. That's all the sand that they use, that they press into shape. They cure it into the position, into shape, and then it's bonded onto this thing. So this right here is what's considered a fine abrasive, and machine shops will usually start with a rough abrasive or a coarse abrasive, and it'll be, you know, twice as coarse as this. It'll have about half as many points in this picture than this one has. So the rocks essentially will be bigger, the grains will be bigger. And then we also have super fine and ultra fine, but they have different numerical gradings on them, and that's a honing stone, and that's what's used to shape the cylinder in dimension and put in the crosshatch. So I think we've gone over everything with cylinders, and what I'm going to do is insert the section about honing, so that'll be coming up in a minute. All right, here we are. We're getting ready to hone the cylinders in the engine. This is the new piston. We picked it up today. It was a 0.5 millimeter oversized, so it's 0.20 or 0.020 inches over. And remember, we talked about ½ inch, a quarter to ½ inch above from the bottom of the skirt to measure your diameter. And you see this one actually has the spots in the skirt coating that are left open, so you can gauge the size of the piston. So what I'm going to do is gauge the size of the piston with a micrometer, just like this here, and then get that measurement and set the dial bore gauge up just like we did on the previous video for the engine block machining. Now there's also a different method of gauging that's available, and this is something that machine shops will use, and this is what's called a bench micrometer, where we have a large micrometer dial right here, and it has its spindle that comes out, then there's a gauge, and then the dial bore gauge sits in the saddle like that. So this dial bore gauge is a little bit more serious than the one that I have. So this is the full dial bore gauge. It's a heavy duty version. It's made by a company called Federal and sold through Sunnin. And you set it up in the setup like this, and use the micrometer to dial in your diameter, and you set the probe tip off the side of that, and that's how this system works. And that's how this system works. So, and this is a bench micrometer. So we're just going to use this micrometer to set it, and we can I'll just verify it on the bench micrometer to make sure we're on the same page. After this, we'll be going over to the cylinder hone. I'll show you some aspects of that and a little bit of the process. All right, so this honing head right here has got an abrasive stone here and an abrasive stone here, and I'll have a close-up shot of that. And this one, and then there's one on the other side that's just a guide shoe. So what's actually doing the material removal is this abrasive stone and that abrasive stone, and it's spinning in the cylinder and also stroking up and down. And it's got to stroke and spin so that it creates the crosshatch pattern on the cylinder wall. So this just goes down into the cylinder. Got a little tighter shot there. There we go. This goes down into the cylinder. I'm going to turn the machine on. You're going to see oil come out here, and that's to flush out the material that's being removed from the cylinder, and to help cool the stones and the guide shoes as they're stroking up and down inside the cylinder. So we'll get to see a little bit of that. So I've done a few seconds of honing there, and what I'm going to do is check to see what the cylinder's dimension is. I'm about 2.5 thousandths over there, and about 2.5 thousandths there. So let's see if we can see this in the shot. All right, so you're going to see the needle sweep, and then it stops and then heads back the other way. And right at that point right there in this direction is about 2/1000 of an inch. So if I go up to the top of the cylinder, we're about 2.5 thousandths. So that means that the cylinder is 2.5 thousandths smaller than our target, and the bottom is only 2 thousandths smaller than the target. As this hones, it's slowly removing material, kind of like sanding on wood would do with sandpaper. It's just this is using an abrasive stone instead of sandpaper. Let's back out. There we go. And we'll watch this cylinder hone. Now I'm taking it to 1/1000th of an inch away from our target, because then I'm going to switch over to a different grit of abrasive. This is what's considered as a rough stone, and I have another 1/2 thousandth of an inch to remove. You can see it goes pretty quick. Of course, we are talking about thousandths of an inch. So right now, it's 1/1000th away from the target, which is 1/3 the thickness of a sheet of paper. So while it seems like it's going quick, it's a relatively quick measurement.